So welcome back to Chem 580. For the class, I have asked the students to do what you might call a quantum mechanics inventory. It's just a few question quiz to sort of gauge the level of where people are coming from, because people come from different backgrounds, and so you can't expect everyone to have the same language, the same set of problems under the belt, and maybe interpretation of my questions was different. So what we're going to do now is we're going to do probably 2 lecture segments here on a kind of like, let's say, summary of even more basic quantum mechanics than the ones that I had done. One of them is I want to make sure that people see the connection between the sort of functions that you often see in quantum chemistry, especially at the undergraduate level, and then the more sort of abstract structure of Hilbert space, which is how we almost always do the real calculations. We don't do we might do integrals, but the integrals are really just to get us numbers that we can plug into linear algebra formulas or linear algebra relationships. And the linear algebra relationships are going to be the ones that are the most practical for us anyway. All right, so the way I'm going to do this is I'm going to start with a problem that everybody already knows, or I shouldn't say that, is traditionally covered in chemistry classes. There's a couple reasons. One of them is because it's the most simple bound system that you can have that resembles chemistry, and the other is because it's actually a useful model of actual chemical phenomena, particularly conjugated, meaning alternating single and double bonds, which are responsible for almost every color that you see, except for the times when it's caused by some metal pigment that's absorbing. Okay, so this is called the particle in the box model most of the time for chemistry people. In physics, they sometimes call it 1D potential well or whatever, and it looks like things you can make in physics called the quantum well. Okay, so the basic model is straightforward. There's a region in space that we'll call X, between 0 and L is how I'm going to call it, where the potential energy function is equal to 0. No potential, where it's equal to 0. And on either edge of the walls, it's infinity. Now, what does that mean? Of course, there's no such thing as infinity potential energy. What it just means is because we set the energy to be so high, it means there's 0 chance for the particle to be here or here. It just can't be there. Right? Not even with all the quantum funny business. There's no way, period, that it could get to this side or that side. So we know that the probability of finding the particle at the wall is also 0, because it can't be 0 right after the wall if it's not 0 at the wall. Otherwise, there'd be a discontinuity. We don't like that in wave functions. Okay, so this is the model. All right, what is it again? What is it modeling? It's modeling, for example, when you have alternating single and double bonds, and you have usually an even number, but you can have as many as you want. All right, what happens, of course, is that the p orbitals that aren't part of what chemists call the hybridization that makes the structure of this thing are left over, and they can delocalize, because in quantum mechanics, if something can delocalize, it will. That'll lower the energy, so you get orbitals that kind of span the whole molecule. So one of them will literally look like this. Another of them will have like a node in the middle, looks something like, the same thing, but there's a node, one sign on the other sign, and so on. It resembles very much the solutions that you get from the particle in the box wave functions. If you do a fancy calculation with real quantum chemistry, you're going to see basically the same thing happen. In fact, I think I'll have over here some video animations of what happens when you really do it. Okay, so we have the Hamiltonian. The Hamiltonian is always p squared over 2m plus the potential energy function. If it's in one dimension, this simplifies things a bit. All right, here, of course, the potential energy function is 0 in the region where the particle can be, so we can ignore this whole term, and that leaves us just with the momentum squared over 2m. The momentum in the position representation is minus I h bar times the derivative with respect to x. Now, there's only one variable, so you don't need the fancy curly things. P squared is just square this, or that means do the operator twice and multiply the numbers by themselves. So that's going to be equal to minus h bar squared when you take care of the I, times the second derivative of x with respect to x. Okay, so that's minus h bar, that's the p squared part. Now the Hamiltonian, of course, is p squared over 2m. So this is going to be minus h bar squared over 2m times the second derivative. Right? That's it. That's the Hamiltonian, the function that tells us the energy. So then we can plug this into the so-called time-independent Schrodinger equation. That's one word for it. It's also just an operator, and we're trying to find out its eigenvalues and eigenvectors. So we can call this an eigenvalue problem. I'm just going to call that EVP for short. We'll have either solved or state lots of eigenvalue problems. So this is an eigenvalue problem for the Hamiltonian. Historically, of course, it was discovered, some sort of special, and so for a lot of chemists, this is the only Schrodinger equation they ever learn about. It's a shorthand notation. It's like H psi equals E psi. All right. For my notation in my notes, I want to do, it's going to look like this. H phi of x equals E phi of x. We're not saying anything about the phi's or the e's or the anything. We just know that we know H. And we know that this is a number. All right. Okay, so then what we do is we just need to solve this. Okay, so how do we do that? We plug in what H is. So H is minus h bar squared over 2m times the second derivative with respect to x of this function phi that we need to find. And that's equal to this number E, which will have units of energy, times the same function again. And what makes this an eigenvalue problem, or it's a differential equation, obviously now, but it wouldn't have been necessarily if this wasn't a derivative. Other operators you could have, is that it's an operator that operates on the function, and you get back the same function just times the number. Okay, so it's almost like the least distorted that the thing could possibly be by whatever operator you did. Imagine it was not this. Imagine it was multiplied by x squared. Well, if it's multiplied by x squared, whatever function you have is now going to be multiplied by x squared and look totally different. Okay? So there are going to be special functions that solve this, and every other function does not. Okay, so let's see how to do this. First thing that is convenient to do here is to write this in the way a mathematician would do, which is to stop all these, ugly constants here and just move the constants over. And the way we're going to do that is just write this. All right, so we have the second derivative of phi is equal to minus 2me divided by h bar squared. All right, so just a simple algebra. And then we notice something about this. Mass is always positive. Energy is positive. It could be relative to some other value. Energy is also can be a relative parameter, but we're taking it relative to the minimum of the potential, which is 0 here. So of course the energy is always going to be positive. And then we have h bar, which is positive. So all the stuff in here is absolutely, definitely positive. There's no question about it. So since we know it's absolutely, definitely positive, we can rewrite this as minus k squared. By making it k squared, we require that it be positive. Now, of course, k could also have complex numbers, but you'll see that those don't solve our problem here. All right, so we write it like this. So now we have an incredibly simple recipe. It says, find me a function where if you take two derivatives of it, you get back a negative number, right? Times that function again. Now, there's not a lot of functions where you can do this. Take derivatives and get back the function again. Now, E does it, cosine sort of does it, cosine sort of does it, right? But sine and cosine are just fancy versions of special cases of, combinations of E, right? So, of course, it turns out to be sine and cosine. So we're going to write down the most general equation. Now, of course, I could multiply the whole thing by any number I want, and that would still be a solution. I could multiply it by a complex number, and that would also be a solution. That phase is undetermined. You can never determine it experimentally, so we will ignore it for this. We can multiply it by it later. You'll see the phase part comes back and becomes very important in time-dependent quantum mechanics. If you're watching these in order, then you've already seen that part. Okay, so we're just going to figure out what this function is, and the claim is it's probably sines and cosines. So let's write down A sine kx plus b cosine kx. Okay, all right, and sure enough, I know if I take the first derivative of sine, I get cosine. First derivative of cosine is minus sine, so I'm going to get back to sine, which is good. Same thing with cosine. Cosine goes to sine, then comes back to cosine with a minus sign. So this is looking like it's going to work. Let's prove it. Take the first derivative, which we can write with the prime, That's going to be a times k times cosine kx plus b times k times minus sine kx. All right, now we take the second derivative, which is the derivative of this. Whoops, there we go. All right, so that just gets me back a negative, minus a k squared cosine kx, there's an x missing, minus b k squared times cosine. Whoops, this should have gone back to sine. You can kind of do it on autopilot, but then you see what happens. Sometimes you crash into a tree. Sine, cosine, kx. Good. All right, now what is this? Of course, this is just, I can factor out k minus k squared, and I see that everything else is the same thing that was in phi. So this is phi of x. So yay, we solved the equation, okay? So we wrote down the generic or the general solution to this differential equation. It doesn't do us any good because we have to plug in something that we know about this system, which is the boundary conditions, right? So you always have to have your boundary conditions. There should be as many as there are derivatives. There's 2. All right, so the boundary conditions that we're going to impose now, they come from science, not from math. This is just math. If someone said, here's your equation, solve it, and if you do math, you get to the end and you stop here. Then you have to ask the scientist, well, how do I choose my boundary conditions? The scientist says, okay, well, infinite potential here, infinite potential here. That means the wave function can't be positive. It can't be anything but 0 in the region where the potential is infinite. All right, well, if it can't be, it has to be 0 over there. So let's look at the left side. This is 0. We know that on the left, the wave function is going to be 0, right? Which we can draw our little orange thing there. And if it was something other than 0, then there would be a discontinuity here. And there's some certain principles of wave functions we say they have to be differentiable. Well, if you have a bump like that, it's not differentiable. So that's bad. All right, so it can't do that. So instead it has to go to 0 somehow. It can come to 0 in all kinds of different ways, but it has to be 0 at the edge. All right, so that tells us that phi of 0 and phi of L are both equal to 0, right? It's like having a string on an instrument like a guitar or violin, and it's fixed at the ends. That's why the solutions look like vibrations on a string. There's no time in this equation, so they're not vibrating, but the pattern that you see will look like the pattern of a string as it's going through its motion. Okay, so let's see what we can do there. The first thing we do is take the easy one, the 0. So when we plug 0 into our equation, which is here, what happens? We're going to put 0 for x, right? So that means we get sine of 0. Sine of 0 is 0. So the first term automatically goes away, and all that's left is the cosine term. Cosine of 0 is 1. So that means this is equal to b, and b has to be equal to 0. So that's the easiest thing you ever did. B is equal to 0. It literally tells you what to do. All right, so the b term's gone, the cosine's gone. Right. Which shouldn't be surprising because cosine, remember, it looks like this. It doesn't go to 0. Nothing you can do to this makes it go to 0 except multiplying it by 0. All right, so let's do the other one. So phi at L, this is the somewhat more interesting one. We already know the cosine term is gone, so we only have the sine term left. So that's going to be sine k times L. And this has to be equal to 0. Now, what do we know about sine functions? We know they go to 0 every once in a while, right? They're periodic. And if you look, you'll see every time it goes to 0, that thing inside it's going to be an integer times pi, okay? So we know that when this is equal to n times pi, we will be guaranteed that this is solved. That tells us immediately that k times L is equal to n times pi, which tells us by solving this, k is equal to n times pi over L. All right, we're making good progress here. So we plug this back into our solution, which only has now one parameter we haven't determined, which is a. So it's a times sine n pi, x is the variable, x over L. Okay, so we have, this is, by the way, just remember n pi over L is k. It's written right here. Okay, so now what about a? Again, we have to ask the science because the math isn't going to tell us. Science is something that we impose on the math, right? And so what we're going to do now is we have to make an interpretation of this function. It's not automatic that we should do anything with this function. It's absolutely a solution to the Schrodinger equation, or time-independent Schrodinger equation. But we want the wave functions or these solutions that we get out to be related to probability. And the way that they're related to probability is in this way. If you integrate the thing squared over some region of space, it'll tell you the probability of being in that region of space. All right, whatever the function is. So this is going to be like the state of the system squared. I'll put the bars in there just in case there would ever be some complex numbers, which when we evolve in time, there absolutely will be. And it's some function that looks like this. If it's in the particle in the box, it should obey the boundary conditions, whatever state it is. And if you want to know the probability of being between here and here, you simply integrate this psi squared in this region from A to B. And that area is equal to the probability that the particle would be found in that region. All right, this is called the Born interpretation, and again, it needs to be put on to the theory. It doesn't come automatically. Now, what are we going to use for A? We're going to find A by saying that we know for sure the particle should be in the box, right? It's got to be in there somewhere. So one thing we know for sure is that the probability of this whole function the area of this whole function should be equal to 1, so that we can interpret this easily as a probability. If it's not equal to 1, it's fine, but we have to divide by it every single time we do any calculation. That's a pain. Don't do that. So make sure the function starts out normalized. You can do that because you can choose this function, this value of A, to be whatever you want. It can even be complex. All right, so we're going to integrate over dx, all right, and it's going to be phi squared. All right. Now at this point, we know that the wave function has a quantum number. The quantum number was not something that we put in by hand. It emerged because of the boundary condition, the L equal that the wave function goes to 0 at L equals x equals L. Sorry, right? Okay, so we're going to put this in. It's going to be a squared sine squared n pi x over L, and this has to be equal to 1. We demand that it's equal to 1. Well, that tells us then what we need to do to make A the right value. So if you work out the integral of this, so 0 to L dx sine squared n pi x over L, what you find out is it's equal to L over 2. Okay? And so what that means is we have, that's the integral part, a squared obviously comes out. So we have a squared is equal to 1 over L over 2, so 2 over L. That tells us that A is equal to the square root of 2 divided by L. All right, so in the wave function, there's the knowledge of the length in two ways. One for its periodicity and the other for its magnitude, its amplitude. All right, so what we have now is a solution to this eigenvalue problem. The eigenfunction there's an infinite number of eigenfunctions and is not bound by anything. It starts at 1, right? And it's equal to the square root of 2 over L times sine n pi x over L. The n values start at 1. They could go to 0. I mean, you can have 0 solution is a solution too, but it means that there's no particle in the box. So that's not a very interesting, that's called a trivial solution. What about the energy? So we want to always have the eigenvalues and the eigenvectors, or the eigenvalues and the eigenfunctions. Here we're talking about functions, so you can call this an eigenfunction, right? Well, we actually know it because it was easy. Since we found k right away, then we can just use the formula that we have over here for the energy, right? We had the k squared here is equal to the stuff in this circle. All right, so we just write that down. K squared is equal to 2me divided by h bar squared. Okay, so we can take the square root, or we can, we want to solve for energy. K squared is also equal to n squared pi squared over L squared. Right, this is the one we want to manipulate. Okay, and so what we can do is to solve this for energy. E, now we can give ourselves a little sub n because we know it depends on the energy. There's a square here. So we have n squared pi squared divided by L squared. That's the stuff from K. And then divide by h bar squared over 2m. And if you work this out, break open the h bar into h over 2 pi, this works out to being n squared h squared divided by 8ml squared. It doesn't matter which formula you use. You probably see the h bar one more in the physics books, and you see this one more maybe in the chemistry books. It doesn't make any difference. Anyway, what you see, our key thing, one is that the energy depends on the square of the quantum number. That tells you that the energy levels get farther apart from each other as you go up in quantum number. That means this is a very anharmonic function, or a set of levels. You see that there's an L squared in the denominator, which means that the smaller you make the box, the farther apart the energy levels get. Okay, that's something that we see experimentally. If we look at conjugated molecules, the bigger they get, the smaller become the energy gaps, even though the number of electrons changes. That's sort of like a linear effect, and this is quadratic. The other thing that you see is that the mass is in the denominator, right? So what that tells you is if the mass of the particle in the box gets larger and larger and larger, starts to look maybe less quantum mechanical, then the energy levels get closer and closer together. Just like if I put myself in a box, I'm in a box, you can imagine I'm trapped inside the screen, right? Well, the screen is macroscopic, the length is very, very large, the energy levels are already going to get close together, and I weigh a lot more than an electron, right? So again, there's no worry about quantum mechanics for me inside this room. Okay, so we have the energy levels, the eigenvalues, we have the eigenfunctions. Now, in most contexts of chemistry, at least that I've seen, this is kind of where you stop, right? You stop, you do this, you draw them. All right, let's draw them. So you put like the energy level, then you show n equals 1 looks like this, n equals 2 looks like this, n equals 3 looks like this, and you get excited about the nodes, and you talk about calculating probabilities and all this stuff. That's fine, nothing wrong with that. In chemistry, it's very natural to want to know the distribution of where the electrons is, what the distribution is. That tells us about reactivity and structure and all kinds of good things. In this class, we're moving more in the direction of time, and so although it's useful to think about what happens if we plot these things, and I'll certainly do it, I want you to think about these in a slightly different way, all right? And the way I want you to think about them is in the following way, which is that these functions actually form a set of functions that is very powerful. The set of functions that they form is precisely one where any function you could imagine that's between 0 and L, and that satisfies the same boundary conditions, meaning that it goes to 0 at the ends, can be written as a superposition of these. Okay? That's very important. So there's an idea here that these functions are a basis. Okay? A basis. This is an important word. They're a basis for any function that you could write in the space, okay, with the boundary conditions. Okay, why that's important is because if you remember from linear algebra, we talk about basis all the time, right? A basis is, for example, in Cartesian coordinates, you have a vector that points along x, which is I hat, and a vector that points along y, which is j hat, right? Those are just names because we know in real space, as far as we know, there's only 3 dimensions, so you can just use I, j, and k. Well, here, how many dimensions are there? There's an infinite number of dimensions because we don't have any bound on the value that n can take. It can go to infinity. So what that means is that we have a space. In this case, I'm thinking of it as functions. We will learn to think of this as vector space that has an infinite dimensionality. That's number 1. Number 2, as I said before, we can multiply this function by any number we want, and it's still a solution. We can also multiply it by any complex number we want, meaning that this could have a complex amplitude. And when it evolves in time, it absolutely will. Okay? So we have a complex, infinite dimensional space, and that is what is known as a Hilbert space. All right? And so if you can be okay with thinking about I hat and j hat as providing a basis, the word is span, meaning that you can then write any vector as a linear superposition of these two components, vectors. You can also think of any function existing between 0 and L in x that has the boundary conditions as a superposition of any of these, and it can be decomposed into those. Right? And then, of course, one of our jobs is to figure out what are the coefficients, what are the expansion coefficients. And those expansion coefficients are very powerful because they allow us to translate from one basis to another basis. For example, as we'll see as we go here, this particle in the box problem is very easy to solve. You see, I did it in one board. I didn't even have to erase it. All right, well, what if I want to change the problem? This is not the most realistic thing in the world. What would be something I could change? Okay, one thing I could change would be to take this molecule, okay, and then apply an electric field. Some electric field along this molecule. Right? An electric field could be very complicated, but if I do a Taylor series about electric field, the obvious thing for me to do is to pick the linear term as the simplest possible term that I would have. So it would be an electric field that varied, you know, as I go from left to right, right? The magnitude of the field. So let's say it happens to go from here to here. This is now my electric field. You think this is a contrivance. It's not a contrivance. You can do this with an STM tip. You can imagine that when a molecule is on a surface, there'll be an electric field from the surface. These kinds of fields happen all the time. In a membrane protein, there's a dipolar field caused by the alpha helices that are usually found in membranes. There are electric fields all over the place. And what do? They add to the Hamiltonian. They change the energy levels. That's why spectroscopy is useful. All right, so if I add an electric field, I could think of it as being super complicated, but if I'm nice to myself, I'm going to make it easy. And I could add a linear ramp. Okay, well now I made my problem a little bit harder. I don't know how to solve the linear ramp problem. I can add it in here as a linear term. And maybe there's some already solved differential equation that, you know, someone figured out in the 19th century when you have a linear function. Fine, that could be. I'm not a mathematician, I don't know. But I'm going to tell you then I'm going to go to the next term in the Taylor series, or I'm going to make this empirical, or I'm going to have it from experiment, or something else that doesn't have a ready-made solution. All right, then we need a way of figuring out what is the solution to the problem when we tweak it a bit. This is very important. All right, well, the neat thing is you can plug this in and you can simply figure out what will be the eigenfunctions of this problem, right? The ramp problem. And the way you do it is by adding the Hamiltonian, the term, the right diagonal, this ramp, and then calculate the Hamiltonian using this basis, provided that you know how the potential energy function interacts with this basis or how it works on it. Well, it simply multiplies by this line. That's easy to do. So you calculate a matrix. Obviously, you have to do this in a finite basis of fixed size. But once you do that, you make a matrix, you find the eigenvalues of the matrix, the eigenvectors of the matrix tell you the expansion coefficients that you need to make the superposition that will get you the eigenfunctions of this Hamiltonian. Okay? So we're going to work out examples of those, and we're going to work on them in our in-person discussion. I'll probably pick a couple of them that we don't do there to put on another lecture segment so that we can get started thinking about this link between a vector space spanned by, let's say, a reference problem or a simple problem, and then a nearby problem. It can't be too different. If it's too different, then we're going to need some ridiculously large number of functions here to approximate the right answer. This is a part of choosing the basis to be appropriate. If you've ever done quantum chemistry calculations, you know this is very important. How you choose your basis is going to affect how good your calculations are. Sometimes there's a way to know, and sometimes you just have to guess, or you have to look at what other people in your field have done. Okay, so we'll work out a few of these. I have actually a nice Mathematica notebook that you can go through that lets you see a whole bunch of examples of tweaking around the particle in the box problem by adding new potential terms, writing the Hamiltonian, diagonalizing it, figuring the eigenvalues, calculating the eigenvectors, and then using them to plot the eigenfunctions of the new Hamiltonian with this change, just as a superposition of these.